about protecting groups. So say you have a generic compound that it has a carbonyl carbon attached to it, and in it there's a nitrogen and then something with a hydrogen attached to it. And then by the same notion you have another of that same compound that it's got a carbonyl and then a hydroxide attached to it. The problem is with this, so say like Grignard reagents, really good for making alcohols and adding, or carbon lithium compounds that are really good for adding carbon to this, but these also have protons attached to them. And remember that proton transfer reactions are way faster than any other reaction that we're going to have in chemistry. So if I treat these with some type of an organometallic reagent, I'm not going to get a carbon attached to there. I'm going to get an acid-base reaction. Acid-base reaction. And that may not be what I want to get done. Maybe I really want to put a carbon attached to this, just hypothetically speaking. The way that you do this, so I'm just going to kind of make some notes here, that if you want to add carbon, if you want to add some carbons, then the first thing that you're going to want to do is to convert your OH group, or anything with that sticking out with that H attached to it, into something less acidic. Maybe an OR group. And what we call this is a protecting group. So I'm just going to say the PG, protecting group. The next step is you run your nucleophile reaction. And then the third step is to remove your PG, or to remove step number 1. And so I guess an example that I could give for this, a commonly used example, is something called a Syal ether reagent. And what it looks like is this. I'm just drawing those carbons to say that I'm leaving it in the abstract. The most simplistic example of this is tert-butyl dimethyl Syal ether, but I don't even see the point in naming that. That's just adding a bunch of carbons. So let's say that I have the formation of a protected. I treat this with something with an OH group. It doesn't matter. Let's say kind of the carboxylic acid. What to do? I then run that reaction with, I'm just going to say SE for Syal ether. Syal ether, and what I get out of that though is my RO, and attached to my R group now, instead of being this, is the Syal ether compound. Cool. And what I can use for this is it adds it to that. And if I wanted to remove my Syal ether, if I wanted to do step number 2, I treat it with some type of a fluoride salt. Fluoride salts are good for removing protecting groups. An example that my book gives is tetrabutyl ammonium fluoride, which seems quite long, so I'm just going ahead and write it that it's some type of a nitrogen there that's positively charged, and then there's a fluorine salt there, and for whatever reason, if I react that with this, so I'm going to switch colors just because I'm kind of getting a mess here. If I react this with this, what I get out of my reaction is back to, I've restored my OH group. Book doesn't really give a whole lot of details on the mechanism behind how that works. I imagine it's probably something very complicated, and I'm okay with missing. I'm okay with missing that mechanism and the steps involved in it. So now let's talk about organometallic reagent reactions with carboxylic acid derivatives. And so I'm going to go ahead and start off with the abstract and then kind of give examples for each of these. So I have a compound here where I have a carbonyl carbon, and then Z being, well, what we're talking about, carboxylic acids or derivatives, which, and this realistically is though just an acid chloride and then an ester. And I run this reaction, and I run it in water with any type of a organometallic reagent. And the outcome of this, depending on, I guess, the identity of Z and then the identity of R, on the reactivity of R, I guess, will give me either a ketone or I could get a tertiary alcohol. So either a ketone or tertiary alcohol. So let's do some examples of these. But what I'm going to do, instead of starting off with the actual reactant, I'm going to go ahead and list the organometallic reagents that we're going to be using for this. So the organometallic reagents that we're going to be using with this is carbon lithium type compounds and then Grignard reagents. So R, Mg, X. The other type of reagent that I can be using is the copper lithium, organocupric, I think is the name of it. Anyways, copper lithium compound, and I'll explain why I'm separating these two again. So remember when we talked about this, that this one here, these guys are way more reactive, whereas these guys are far less reactive. So let's say that I react either one of these with, and I'm going to switch colors just because I'm getting bored, say an acid chloride or an ester. I'll start off with the esters over here. So I have my ester here, and I go ahead and run this reaction with, I'll say carbon lithium just because it'll save me the space. A carbon lithium compound, that's going to be a nucleophile. It's going to do a nucleophilic attack, which we've already talked about, the generalized mechanism behind how that works. And what you get out of that is, and I'm going to change colors in magenta so you can see that that's where that came from. If you're wondering the mechanism behind this, I believe I've already given details of it, but basically the carbon binds here, the lone pairs come here, and then they come back down here, and then that leaves. I've done mechanisms behind that in other videos. Watch them if you need to. Anyways, and so whenever I'm doing any type of these reactions, just like with lithium aluminum hydride, I'm going to assume that I have an excessive amount of reagents to work with because these are so reactive in species. So I run it with that, and I'm just go ahead and put it over here that obviously I'm running this with water as a solvent, and then it does exactly the same. It runs an SN2, not an SN2, sorry, a nucleophile attack, and then removing it up there, becoming an anion, which is going to be deprotonated. I'm kind of not redrawing the same mechanisms over and over and over again just because it's getting kind of redundant at this point. But what you have at the end of your day is, if I can find my colors here, there's an R there, there's an R there, and there's an OH. So what we have here is a tertiary alcohol. Now, if you look at one of our intermediates, is whenever I talked about the two types of reactions that we could get with this, we could either get a ketone or we could get a tertiary alcohol. This ketone is an intermediate of this reagent. And what was interesting to me is whenever I was first going through this, I thought, okay, surely I could isolate this in my mixture, but it defeats the purpose because you don't know how much. It's not like a 1-to-1 ratio of this. When you're working at this, I have not once worked with balancing my equations at all in organic chemistry. That's just not something that we've talked about. But let's say that I wanted to make a ketone with this. Well, I would use this. This is a much less reactive species. So I'll say, and it could be with an ester or an acid chloride. The OR group and then the Cl group, those are both leaving groups. Those are both good at flying off. So I'm just going to show it with a acid chloride just to be diverse. And I'm going to stop using abstract terms. I'm going to say CH3 reacting with copper lithium there, doing what it always does, giving us a R group or a methyl group that's going to act as a anion nucleophile. And what I get out of that is not changing too much here, but what I've added there is a CH3 group. I meant to draw these in magenta. I'm just going to go ahead and draw the methyl groups in magenta. And I have 2 of them. Hopefully that's not too gross to see. But you can see that I've used a methoxide anion as a nucleophile in this reaction here. So this way, I only have one product that I have to worry about. I know that this is the only thing that's floating around in my reaction mixture, whereas with this, I might be able to isolate this, but at the end of the day, at equilibrium, I'm going to get more of this. So obviously, this is much less reactive. This is better for making ketones. These guys over here are much more reactive, and they're better for making tertiary alcohols. So now I'm just going to talk about organometallic reagent reactions with carbon dioxide and epoxides. And if you understand how nucleophiles work, you'll understand how these reactions proceed. but it's never hurts to review. Got that ACS exam coming up, which is something I probably should be stressing more of. But this only works when, and don't ask me to explain the exact details of why, but this is only works with Grignard reagents. Only Grignard reagents. And so what we get out of this reaction, I'm going to go ahead and just draw the overall thing. We have our Grignard reagent. We go ahead and react that with some carbon dioxide dissolved in water. And what we get out of this is a carboxylic acid, which is really nice that we can make that. Remember, we talked about all the types of reactions that they can do. So let's just go ahead and draw out the mechanism for this. So here's a carbon dioxide. If you're having trouble understanding the reactivity of anything, I advise you all to draw out the secondary Lewis structure, or the minor resonance structure of it. And I'm going to switch colors just so that we can, I don't know, not get lost so easily. So there's my Grignard reagent, and what happens is the nucleophile, the carbanion nucleophile, is going to attack this carbon here, and it can you arbitrarily break one of the bonds in the oxygen. I'm just going to break the one on the bottom, and what I get out of this is a carbon with an anion. I'm going to draw my carbonyl over here just to make room for it because it's not really that important. But attached to it is my R group floating off somewhere. Now I'm also running this reaction in water, so I bet you can imagine what's going to happen here. We're going to steal a proton off of water. This chapter isn't difficult so much as it is just multiple reactions that one needs to learn. And so what I get at the end of that reaction is a carboxylic acid. Now, let's talk about what we can do, reactions that we can have with epoxides. And it's your generic nucleophile reactions. Remember we talked about using lithium aluminum hydride nucleophile reactions to do this. Well, now we can use, say you wanted to create a more stable compound, you can add R groups to this. So this works with either Grignard reagents, lithium reagents, even organocupric reagents, or copper reagents. I don't know what the specific name is. Shakespeare was a genius, because what's really in a name? And as you can imagine, I'm not even going to really, well, I mean, I guess I'll go ahead and just draw out the mechanism. Seems kind of tedious at this point, but so I have any one of those. I'm just going to abbreviate in the abstract as RM. I go ahead and run that reaction in here, associating it out there. My next step gives me a carbon. There's my wedge. There's my dash. There's my R group attached to it. There's my carbon. I was thinking ahead of myself. There's a wedge. There's a dash, and then there's an anion, an oxygen with a negative charge. And I'm running this in water, and if you don't know how this works at this point, I pity you. And what you get out of this is, I can switch colors, whatever, depending on the identity of this, you get a more stable compound. You've added an oxygen, hydroxyl group, sorry, and you've added a carbon to that. All right. So